So in this video, we learn how to use Wildkatze solver in client server mode, and also we look into the very basic concepts of Wildkatze solver. So for this purpose, we go here, and there are two articles. The first article is that summarizes the basic concepts, and the second article where we create a basic simulation using the mesh provided to us here, and then we learn how to use this concept in the action. So the core concept of Wildkatze is very simple. In order to solve a physics model like flow, energy, turbulence, etc., you have to define the physics model, and the physics model is defined on a region set and a phase set. So in order to use any model, like let's say you have a flow model, you need to define a regions on which this flow model will be solved and the phase on which it will be solved. So the phase can be air, water, or some name that a user decides. So to create the region set and the phase set, we load the mesh, and the load has the regions in it. So we can select a combination of them and create the region sets. So as an example, let's say you load a mesh that has 5 regions in it, and you are trying to do a simulation which is conjugated heat transfer, and all the 5 regions are involved in heat transfer calculation. But only 3 regions, region 1, region 2, and region 4 in this example, are the regions where you solve the flow. So in this situation, you create a region set 1 for the flow regions, and then you create a region set 2 for all the regions, and maybe region 1 has, for example, some chemical reaction going on where we can apply the chemical reactions, and so we can create a region set 3, and all these 3 region sets we would like to later on apply a different physics model. So the energy model may be for the region set 2, region set 1 gets the flow model, and region set 3 gets chemical reactions. For the phases, they are not present in the mesh file, so we have to define them ourselves, and this we define ourselves, and then we create the phase sets using them. So the multi-phase concept in Wildkatze is that imagine that you have created 5 phases, and you can then create phase sets using them. As an example, let's say you have a 2-phase flow, a typical interface capturing method, and then these 2 phases, the flow is solved on a mixture phase. So there has to be a mixture phase or a phase 1 here in this case, and it depends on, let's say, another 2 phases, its properties like viscosity, density, etc., and they are calculated as a mixture or weighted sum from the volume fractions from the phase 3 and phase 4 in this example. So, and then let's say the phase 4 of them is again dependent on some properties of other 2 phases. So we can create a chain dependency of the phases like that. And a typical example would be when you have a phase which is moving, like a 2-phase simulation, and one of the phase is going through reactions. So in that case, that phase is getting its properties itself from other phases, and then the mixture properties are constructed from it. So this is how it would be. And once a user defines the phases, then it can you can define the phase sets, and once you have the phase sets available, then you can create the physics model. So this whole concept is at the core of the Wildkatze solver. So you create a region set, you create phase set, you can define the physics model, and the solver will iterate them. So it's simple enough. So this is the core idea behind Wildkatze solver. So to run the solver in client server mode or GUI mode, once we have to start the client, and then we would like to start GUI, and they both will be connected. So let's see. So first of all, we download the example mesh that is provided to us. So I download it, and now I can go to the download folder, and I unzip this file that we downloaded here. And in this case, I will copy two files, the mesh which is provided in Fluent format, and this run.txt which will help me load the case later on. So I go to home, create a folder, and I copy it here. Now you can see that we are provided with the mesh in Wildkatze format also. The reason why I only copied the mesh formatted file, because many times you would like to convert the mesh from Fluent or StarCCM or OpenFOAM format. So in this example, we see how we use the Fluent format file. So we have a Fluent format file here, and we will convert it. So first of all, let's go convert that. So try, and here we have this Fluent format file, and converting it is easy. Solver.sh -lc went to the mesh, and the file name without the extension .msh, and it's converted. Now solver.sh is part of the setup that we suggest user can create, and we have it here in the binary, which basically put the path to the MPI run, then provide number of processes we are using, then path to the solver, and the path to the license file. So user do not have to write these things again and again, so we can put them in a script file. Similarly, the solver.gui just simply run the jar file from its location. So come here, we have converted the mesh file, and after the conversion, we see that we have two files produced, the info.bmesh and .bmesh file. The .bmesh file is binary file which contains the heavy data, and .info.bmesh file is the information about the mesh. So you can see that number of regions present in this mesh is 1. The name of the region is fluid, type is fluid, and these indicate the boundary conditions. We have triangle, outlet, inlet, symmetry. It's a wall type, it's outlet, it's inlet, and symmetry. So simple enough. There is a obstacle called triangle, and in this example we will be calculating the force around it. So once you have converted the mesh, we will start the server in one of the console. So solver.sh -s 5010. 5010 is a port number, which can be any number that user can choose. I just randomly putting one. And you can see after this, the Wildkatze will tell you that server has started here. And to run the GUI, simple enough, solver.gui.sh, and we have the GUI running. So this is our client, and this is our server at the port 5010. And we have to connect them to start communicating, which is here, and I put the port. And you can see that client, from the server side, we can see that it has accepted the connection. From the client side, we can see that this is connecting. Now, in order to start a new simulation, we use this first or second icon here, and as soon as we click, it will ask us to provide the mesh file, which we go to the folder and we pick the .info.bmesh file. And once we select it, it has created me the basic simulation tree, which has various things in it. And you can see the first is simulation, which is also provide me the option tree for the simulation related options, like I can choose transient or time step size I can change here. Anyway, so this grid node will provide me the number of regions here and the information about the grid that I just loaded. Based on this, we will be setting it. Now, as I mentioned earlier, we will need region set and the phase sets to define the model. So you have a region, phase, and the models. In the basic setup, you see a lot of other things, like the first icon for here is for code library. This is for user coding. If a user wants to do advanced work with Wildkatze. Wildkatze is, in reality, is a finite volume framework. The CFD solver is just an outcome of that, but it is designed to be as a finite volume framework, and people can use it to do their own research. So users do not have to use all the or any of the model provided by the solver. This is a finite difference grid. You can generate finite difference grid and do finite difference models here. We will not be doing for this tutorial, but usually this is also available. At the region node, you see region set, immerse region, partial region, region to region, and region interfaces. For this, most important are the region sets and the region interfaces. For the simulation where you have multi-region case and you want to define region interfaces, then you will be using this. And you can create one by one or create them by the file. By the file will be more efficient. And I will not touch this advanced options here. This is a basic tutorial. So for the phase, we have the phase and the phase definition here and the phase sets. And the phase to phases is needed for multi-phase simulations. Then you will have motion. You can define a simple motion and then connect it to the regions and define motion objects. So you can, let's say, do a rigid body motion or immerse boundary motion like that. Here at the species, you can load the reaction file and also do reactive flow, which we are not covering here. And then you have the models and the finite difference model, and finally the node for the post processing. So it's a very simple, all the basic stuff is here. So we go ahead and define the region set. In this mesh, we have only one region, so we select this. Here we can change the name for the region set, but I'm keeping it default, and I created, and now we have the region set available. Same we can do for the phase, but we need to define the phase. As I mentioned, there are no phases available now, so I create one, and it is named phase 1. We can double click and change the name. I change it to air, and by default some name is given, and you can always change it. And at the moment there is no material, so if you right click, you see few options. You can add the material, add the species, you can add the specialization to idle gas, noble, able, etc., and some population balance things. So a lot of advanced options. In this case, we just add the material, and this material does not have any properties, so I will copy from the database. You can see the air and water is provided. Here you can choose power law or highly viscous flows also if you want, but I choose air for now, and we have the air properties available here. And you see here on the right side there is this option tree. So whenever you click something here, if the option tree is available, it will be shown here. Here you can change the values, like for example, if I want to change the density, I can change, let's say, to 1.5. I can change the viscosity, let's say I change it to 2.5. And other things I can change. So we have the basic phase available to us. So I can create now the phase set. There is only one phase, so I will choose this, select. And I'm not changing the name, but here you can change the name also, and I'll create it. So we have the phase set available. So as soon as we have the region set and phase set available, we can proceed to define the model. And for this, I click and do pre-initialize. Pre-initialize stage is very important for the solver because here it allocates the storage managers. Without this step, you cannot define any model. So we create a model set, and here we can add the model. So we can click on the add model, and you see we have now phase set, region set, and there are various models available. You can see this is polar malus, turbulence, this is VOF, you have conjugated flow model, immerse boundary model, energy model, multi-fluid model. This user transport model is where user can add user coding and specialize. And we have many models like K alias, K epsilon. So acoustic potential. And so in this simulation, I want to run the flow and turbulence together. So first I will add the wall distance model on it, and we added the wall distance model. Then I want to add the flow model. The order is important because in this order the iteration manager will solve them. And now I will add K omega turbulence model, and it is added. So you can notice that all these models are presented in the same way. And if you open them, you see there is they are on the same pattern. And this is by design. So the reason why this is done so is that we want user to change the setting in the same way, so that every time a new model is added, he does not have to go to user guide and learn where the options are. They are all presented always in the same manner. So once you learn this basic GUI, you should not have to learn again and again more things. So this will save a lot of learning time in future. This is why. And all the model options are presented by this model condition, and you open it and you see the phases are, model conditions are for the phase. So if I click on the air, for the flow model, I can see for the air there are options available here. And you see, I can change the option. Let's say I change it to bounded central scheme. So right click and select, and now the bounded central scheme is selected. I can change the, let's say, momentum under relaxation to 0.8. I can, let's say, change the continuity under relaxation. Let's say I reduce it to 0.2. So you can double click and change the value. So it's simple enough. And boundary conditions are provided here at the boundary condition node. And you see for each region there are boundaries available. And for each boundary, for each phase, there are options available. So you can choose, let's say, wall type to no slip to full slip, or there are various options here. Then let's say at the inlet, I want to change it to 10 meter per second. You see the inlet type is set to velocity magnitude by default. You can choose component and other options. I will simply change the velocity to 10 meter per second for this example. And same thing one can do for K omega turbulence model. The same options are available here. You see, you can change the parameters. So the idea is that all these options are provided at one place, and you don't have to search where to provide them, how to do it. They are all here. And as a option tree. And then the boundary conditions are here for k omega. They are same way they are provided. It's consistent manner. So we will just leave like that. And now once you have defined the models, you can go and define for the post processing. Let's say we want to export the forces. So I create the report. I call it force report or report force. I can select the triangle. This is the wall where I want the forces to be exported, and I can select the force here, and we are good to go. Create, and the report is created. But for this report, I will create a monitor, and this is going to be a transient simulation. So I select it based on time, and I call it monitor force. Select the report that we created and create, and that's all is needed to export the forces. And then we should change the simulation to transient type. So this is where we click on the simulation node here, and the global simulation related options are available here. I select on the right, click on the transient and select it, and now we see the transient is selected. I can change, let's say, max iterations per time step to, let's say, 6 here. One can choose, let's say, variable time step by setting it to 1, and then change the current number here to control the time step. That's possible. There are other advanced options which I'm not touching for this video. So okay, so far we are able to define the models. Now we want to also export the results. So let's say I'm exporting the results on the time step basis and with the time frequency, because the simulation is transient. So I set the value 1 to power 2 minus 2 because the time step is 10 to power minus 3. So every 10 time steps it should save. And I say create goal. This is done. And you can choose field view also, but I'm using inside goal. So now the whole setup is done. This is all. So to summarize the process, we create the region set, we create phase set, we create models, and we set up the post-processing, and that's it. This is all is needed. At this point, before you save, you should initialize. This is the button to initialize, and I click it, and I see here that the models initialized is appearing. And once this appears here, that means the simulation is initialized. Sometimes if the mesh is very large, then this may take time, because in the background it may be solving the wall distance and all this type of things. So you might have to wait for this to appear. For a simple mesh, it will immediately come here, and all the models are still there. The simulation tree we can save now. To save the simulation tree, obviously we will use this save button, and we go to here, this folder, and I save it as a try.stree. The extension is stree, that is simulation tree, and we saved it. While we can run the simulation from console, we can also run the simulation at the GUI, and this is done by, after initialization, this is a button to iterate, and if I press here, I can see that it's doing some iterations. I can stop, and here it's writing the report, and same here it's writing the residuals. It's not exporting the force data to the console here, which is not really needed. Also, when the simulation is running, it's supposed to create a few things. It creates you a cell quality summary. In this case, the mesh is good, so there is no cell which is bad. So pretty much okay, no problem. So now I can say I have already saved it, so I can exit from here. We can actually post-process the data. This is the button to export the post-processing here. Let's say we save results, and the results are exported here. So since the setup is done, I will come out of the GUI and I can check the results that we exported. And this is wall distance. We can plot the velocity. We can plot pressure, effective viscosity, etc. So now we want to run the simulation after the setup. So if we want to continue this, I copy this run.txt. And here you can see that the mesh name is already set to correct value, and the simulation is output.s here, but I will set it to try because we save the file as a try.string, and this command will read. So we save it. And to run the simulation now, we just say solver.sh and tf run.txt. tf is short form for process file, and so it will process all the commands given in this run.txt and it loads it. So once the mesh is loaded here, or the case is loaded, we can simply iterate. Let's say we iterate for 50 time steps. And we can see that it should be exporting the residuals here. It exports the monitor in a .ps and .csv file. So we already by default export some .ps files that you should be able to drop into the presentation and should be good to go. That is the idea. But you can specialize it by using the CSV or D2plot, one of these way. Anyway, so we have run some time steps, and if we want to check how the results were, I can again export the results here. Let's say the export minus inside results, and it has exported me the results. I can check them. Let's see, started to develop robotic shading. I can, let's say we want to save the result simulation so that we can resume, and that is done by save restart minus bin rest bin, and we have saved it. I can exit and see that we have this file saved here. So let's resume the file that we just saved. For that we do again solver tf run.txt, and this will load me the simulation that at the initial stage. Now I load the restart file, that is read minus restart minus bin rest b, which is the file name that we saved, and it's loaded. So we can check, iterate 1, and you see that it started from time step 51. So we can, let's say we run it another 25 or 25 time steps, and once we have run this many time steps, let's say we want to change some option. Let's say we want to increase the number of inner iterations per time step. So for that you press options here, and the solver will set up the options related to simulation. You can check it, op minus list, and it lists me the options available here. And if I want to, let's say, decrease the number of max inner iterations, then this is where I will do. So it is op double and set it to 5. And op double is to set a value. Op minus tie will be to set an option. So we will see that later. And op minus list shows me what happened, and you see now the max iteration per time step is set to 5. Okay, so here we can change these options. We can change the time step size. That would be OP double, time step size 0, and some value, let's say e to the power -4, and I can iterate further. Let's say I iterate 5. I can change this back to the 10 to the power -3. Let's say OP list, OP double, back, and OP list shows me that we are back to the time step that we started with. So I can run, let's say, another 25 time steps, and while it's running every time, it's also producing us the force data. For example, if I continue running it, then it will update the graph there. So imagine that you want to now change the options in the model. So for that, you have to do model list. It lists me the hash of the models that we have added, not the name. So they are stored in a hash table, so like that. And to change the option for, let's say, for the flow model, I do flow model minus phase minus options model hash. The second model was the flow model, so I use the second hash. Add the phase name, and you can see the options are, and all these options are available here. And I can change, let's say I want to change the convection scheme to a second order upwind. At the moment, bounded central is used, so OP type, not the OP double, OP type, and convection scheme, second order upwind. I remove the comma here, and OP list. Now OP list now updates it and shows me what is set. So you see, convection scheme is second order upwind. Let's say I want to change pressure interpolation from body weighted to standard weight, and again OP type, pressure interpolation, choose standard, and it is set. So this is how you can change the various options. Even when the simulation was running, you can pause and do it. So let's say we run this simulation a little longer, and imagine a situation where the simulation is going on and you want to pause it and change the option. So how would you do that? So for that, let's run it for longer time, and let's say iterate and give a very large number of iterations so that it keep on running. And you see now, once it is running, we check, we'll see that the forces should be updating whenever it will write this force. You see now this updated further. And similarly, the residual will be updating here. So now we want to pause this simulation and change the option. Let's say we want to see how the convergence in the continuity was, the AMG. So for that, I would do touch Wildkatze dot pause. So I create this file Wildkatze dot pause, and when this file is there, the solver will pause. I should remove this file before I continue, and I remove it. And now we are here. I can say OP list, and we are still in the flow model setting. If we were not, we can choose it. So I want to see the verbosity of continuity AMG. So let's set it to 1. So OP double to 1, and OP minus list, and you see the verbosity for continuity AMG is set to 1. That means it should print me the residual. So let's see. I do iterate 1, and now you can see what happens. So it's now printing how the AMG for continuity was doing. This was your initial error and how the error was reduced. It took 2 cycles to converge 10 times. And it's using AMG as a preconditioner. It's a bi-conjugate stabilized solver. You can change this default. So OP list, and you can say, okay, I want to use just the recycle AMG. That you can do OP double, like that. I'm not changing it here, but this is how you would be changing if you want. And you can also export the results here again. Export and cite results, and you can check it. You can save again before you export. Save minus restart minus bin. I say rest b to the second file, and you can save it here. So this is a typical workflow with Wildkatze, and the Wildkatze console, you can do a lot of advanced things. Not only these small, there is a document available for it, and you can use. And to exit the solver, I can simply say exit, and we should be out of the solver. And once it is exited, it's exporting the monitor, residual, etc. And this is what it was. And now, since we were running the simulation, we also produced a lot of transient data to post-process. You see this? And we can visualize this in Paraview. So here, and you can see, I check this, and I can see it does the vortex shading. And you can check various things like turbulent viscosity, K, omega, pressure, all these things are available here. So this is how you can do the transient post-processing. So this is pretty much it as a summary of the workflow with Wildkatze using the GUI. If you don't want to use GUI, then you can simply run the whole thing from the command prompt that is discussed in another tutorial. So I would say thank now, and I will shut down the recording.